Hi, everybody. Oh, man. Hello. Hello. Happy Thursday, everyone. Happy Thursday, end of April Thursday. Tomorrow, I think, is what, May 1st, right? Yes, it is. And I hope everyone watching is doing all right. I appreciate you watching if you're watching live, of which I think there might be one person right now, which is very nice of that one person. If you're watching this after the fact by watching the video, this is nice. Welcome from hello from the past. If you don't know who I am, I'm Dr. Kevin Hainline. I'm an astronomer who lives in Tucson, Arizona. I work on a space telescope called the James Webb Space Telescope, and I think a lot about astronomy all the time. Mostly I think about galaxies, faraway galaxies and black holes. But in the last couple months, since we've all gone into quarantine, I've thought a lot about how I could talk to people about other parts of of astronomy. And so I've been doing like a little kind of every other week lecture series. It's like an hour long, where we kind of fly around using a piece of software. That's what you see behind me, called Space Engine. Space Engine kind of simulates the motions of planets and what they look like, and if you can fly around on them, which is pretty cool. But also, I do this thing where if anyone has questions about astronomy, something they've seen in the night sky, they can ask it in the chat, and I'll hopefully answer it. We'll see how that goes. But in the meantime, a couple weeks ago, I did just kind of a generic Ask an Astronomer thing. Then a couple weeks later, I did a talk about like our solar system. I did one about stars and how stars live their lives. And today I thought I'd talk about other solar systems, not just our own. Our own is known pretty well. Oh my gosh, hello, Crazy Missions. You are talking to me. That's how it works. There are our own solar system is pretty amazing, and we're kind of it's next door essentially, so we know it pretty well, and we've sent spacecraft there. But as we talked about in a couple weeks ago, there are so many other stars that exist, and so you might be wondering, are there other planets? Are there other planets like our planet? And that's a pretty good question to ask. So to that end, let's get going. Let's introduce you back to Space Engine. So hopefully you can all see this. This is Valles Marineris. We talked about this a couple weeks ago, but this is a canyon on the surface of Mars, and you can see that you've got the faint haze of Mars's very limited atmosphere and this beautiful canyon right on the surface. This is transitioning into sunset for Mars right now. There's the sun, which is pretty incredible. So let's zoom out and look at our solar system zoomed far out. So I'm going to turn on the button here that puts on the orbits of the planets. Now you obviously can't see these normally because there are no floating green lines in space, but they help us so if I really increase this, whoops, there we go. Here we go. If we kind of get really right up here, you can see all the planets as they move around. All right, so these 4 planets are interior: Mercury, Venus, Earth, and Mars. And then we get the asteroid belt, then Jupiter, Saturn, Uranus, and Neptune, and then a bunch of Kuiper belt objects at the edge of the solar system. So this is everything, right? And the thing is that, when you live inside of it, it's pretty easy to see the planets, right? Especially if you sit on the planet Earth and look around at night. You can see planets like tonight. If you live in the northern hemisphere, you can walk out at night and see Venus just with your naked eye. Pretty easy to see planets. Now the question is, how can we find planets on other solar systems, like around other stars? Well, here's problem number 1 with that. The kind of main thing about that is that if we zoom out, if we really fly away, so we're pretty far from the sun. If I turn on my information here, oops, here's the sun. So we're currently located 1,000 times farther from the sun than the Earth is from the sun. So over here on these says distance is AU. That's distance from the Earth to the sun. And so if we start flying out, you can see that we're getting farther and farther and farther away. So let's go like, say, the distance of, I don't know, the nearest star. So right now, we're only 0.13 parsecs. All right, let's go to a parsec away. 0.3 parsecs, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. So we're currently at 1 parsec. We're looking directly down on our solar system, right? If I center the sun and we turn on our telescope here, really got to turn it on quite a bit before you can start seeing the outer planets right there. But you can, right? If you have a pretty good telescope and you were 1 parsec away, which is about 3 light years away, you could hypothetically see and take pictures of the planets. But it's really tough, okay? And the thing is that if we go even farther, go to like 3 light years, what's this? This is Alpha Centauri. So there's the closest planet, right? So if we're sitting at Alpha Centauri, so let's get a little closer. And now we're still pointing. You got to really, really zoom and zoom. Look at how much zooming we're doing until you can see the planets, right? And even then, can you see an Earth? No, it's really difficult. You got to get really in there, right? Almost. There's where we can see the Earth. The Earth is one of these layers right there. That's the Earth right there, okay? I've done an enormous amount of zooming to get there, okay? Look at how much zooming. So it's interesting. I'm getting some information that I'm not dropping any frames. Interesting. I don't know why that's going on. So the big problem is that planets are really small and stars are pretty bright, right? If we put this and crank up some of the brightness of the sun, right? So we're really zooming in. The thing is, the sun is too bright. It's so bright that, unless you zoom quite a bit, you're not going to see anything really close. Like, you got to really get close, and the sun is still incredibly bright. If you were to take the sun and make it as bright as, say, like the spotlight that you'd have at like advertising a car dealership, a planet, the way that it glows, would be like a firefly zooming around the edge. Very, very difficult to see on the edge, of an incredibly bright object. So if I pointed like a spotlight at your eyes and then had like a tiny firefly floating around the side and said, "Can you find the firefly?" Very difficult, right? Planets don't make their own light. They kind of do because they're a little bit warm, but generally they reflect the light of the host star, or if they make light, it's their warmth from the sun's light, which they're re-radiating in the infrared. But generally, planets aren't very bright. They're really small. They're very close to the star, seen from very far away. Like, this is the best case scenario for us. For most stars, they're much, much, much farther away. Right? If I motor out to like 10 parsecs here, and now I'm continue to try and zoom in. We're zooming and zooming and zooming and zooming and zooming, and now finally you can see Kuiper Belt objects and stuff. And finally, it's really ridiculous how good of a telescope you need to do to take pictures of planets. So when it comes to finding planets, you can't just go and say, all right, well, let's look at every star and just like get the best telescope we can and find the planet, because it turns out that our telescope's resolution limit is actually not super great to find planets. There are some exceptions. There are some planets that we have directly imaged. We call them directly imaged planets. I always see a big bright star which is bigger than all the other stars. Is that a planet? I think right now, Craze, if you are going out at night and looking out towards right where the sun is set, and there's like one that's like super bright looking star, that's Venus. You could tell it's a planet because it won't flicker in the night sky, right? And so luckily those are the types of planets we can see. But planets like around other stars, pretty difficult. We have taken direct images of planets. The question is, how do we find planets then? Well, here's a cool chart. Are you ready for a chart? Maybe you're not ready for a chart. I like this chart. Here's a chart. Okay, so on this chart, you have date down here, and then here a number of planets we've discovered, right? So for a long time, the number of planets we discovered was 8, because those are the only planets we knew of in our solar system. So we've removed those out, and these are extrasolar planets, number of planets outside of our solar system that we've discovered. And so you can see that 1988, 1989, 1990, 1991, we had a couple, but then in the mid-2000s, if we look really far over here, the mid-2000s, you can see that we suddenly have tens, and then eventually there's this incredible boom, thousands of planets. How do we find them? What happened in the 2000s that allowed us to find all these planets? These are planets not in our solar system. They're planets around other stars, exoplanets. Also, why are these different colors? Well, what's important is that the different colors essentially tell you how they were discovered. And the green is what we call radial velocity or transit, and the red is what we call radial velocity. Right? And I'll explain what those mean in a second. But essentially, know that the discovery of other planets around other solar systems is only, most people watching this, unless you were born after 2006 or 7, you were alive in the renaissance of, or the not renaissance, the birth of this entire field of looking at this. This is a very, very cool field in science and astronomy right now, is to look and find these planets. And so the question is, what happened? How did we do this? What did we discover as astronomers that allowed us to find planets outside of our solar system? Was it that we got better telescopes to take better pictures? No, it was the fact that we got better telescopes and instruments that allowed us to do some cool techniques, and I'll explain what those are in a second. So let's turn this window off. Let's go and look at our sun. All right, so let's go to our sun again. Again, we have to fly quite a bit to get there. Whew. I've turned on the brightness quite a bit. There's our sun. I'm going to turn these lines. Actually, lines are still on right now. So here's the sun. And the thing is, what we would love to do is we'd love to see if there's some sort of way in which we can infer that there are planets because we can't take pictures of them. What's some way we could look and see if there are planets around a star without actually being able to take pictures of the planets around a star? And you can think about this in a way where you're like, well, okay, let's imagine that you want to know if someone has children, right? What are some ways, but you can't ask them if they have kids, and you can't see the kids themselves. What are some ways in which you can infer that a person has children, right? Like maybe you could look at the books, like receipts at a bookstore and they've like bought children's books, or maybe you could look through, like there's ways in which you could infer that they have children, right? Like maybe you could listen really hard and hear the children. But like for a star and planets, you want to find, is there some way that the planets are having an impact on the star? The star, we can see stars pretty well. Is there a way that we can see that the planet is having an impact on the star somehow? Okay. And so here's the first way of doing that. So what I'm going to do right now, I'm going to turn the brightness down quite a bit so we can really see that star there. So there's the sun. I'm going to make time go really fast. Okay, so I'm going to essentially just make time go really fast. You're going to know time's going fast because you can start seeing the planets moving, right? So there's the planets starting to move, right? Mercury is really orbiting around there, 88 days, right? Earth takes 365 days. So this tells you how fast we're going because, 1 year compressed. So there they go, right? And now, if we move this a little bit out like this, I want to try and do this. I got this earlier, and I don't understand why it's not doing it right now. If I center this, whoa, oh gosh, that is not what we want to do. That is the worst thing I could possibly do, is make it so that you're right on the sun, and the sun is changing really fast. Let's turn off this. Let's sit right there. Click on this. And let's make time go again really fast. Okay, so we've got time going really fast again. Huh. Wonder why it's not doing what I wanted to do. It was doing this earlier, and I am frustrated that sometimes it doesn't. Let's look at the Earth really quickly. Because this will show what I'm trying to show. All right. So here's the Earth, and there's the Moon, and I'm going to make these go really fast, okay? So as the Moon goes around the Earth, I want you to notice what the Earth is doing. Earth's in the very center there. Notice the Earth is wobbling, right? If I speed it up, whoop, 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 the Earth's wobbling. It's not somehow like staying exactly at one spot as it goes around the sun. It's kind of going in this little wobble, right? What's going on there? Why is it doing that? I was trying to show you that the sun does the same thing, but Space Engine wasn't being nice to me right there. And so, for some reason, the Earth is wobbling. And if we watch the sun, so if I center, whoops. Oh, let's go there. Stellar Berry Center. I really go there. I don't know why the Stellar Berry Center is not showing the same scenario. There we go. Look, the sun's doing it too. Finally. I guess you just have to like turn on quite a bit. Notice the sun's wobbling. We've got all the planets really motoring, right? We're going very, very fast. The sun wobbles. Weird, right? So the sun is doing this wobbling thing. Why is the sun wobbling? Let's stop this crazy thing. Well, the reason the sun is wobbling is because the planets are pulling on it. The planets right now are being pulled by the sun, which is why they're going in a circle. They want to go in towards this way, but they're zooming out to the right really quickly, and so they kind of go in this orbit around here. All right. Craze asked if we could live on the moon. The moon's pretty cold, doesn't have an atmosphere, and there's very little water, so it probably wouldn't be the best place to go live right now. I think that there's a little bit of ice, but we'd have to probably bring a lot more of the water ourselves. And so that'd be constantly replenishing, and also it's very cold to be constantly indoors, so kind of like this quarantine, but you can't go out at all ever, maybe in a spacesuit, and also there's a lot of danger of radiation from the sun. Speaking of the sun, so the sun is pulling on the planets, right? Gravity is pulling on the planets, but the planets are pulling on the sun just as well, and so the actions of all the planets as they move around causes the sun to wobble. We call it reflex motion. It's reflective of the fact that it's pulling on the planets. This is a Isaac Newton thing of every action has an equal and opposite reaction. Because the sun is pulling on the planets are pulling just as hard on the sun. And so the sun wobbles. And so when we looked at it really, if we zoom in and we drop this a lot, if I do this, it's going to, we go really, really quite a bit. You can just see the sun wobble, wobble. And it's kind of a weird wobble, right? It's not just all one word. It's like it kind of motors around. Like if I put my mouse up here, you can see it's not exactly moving in the same circle. It's kind of making like a spirograph pattern. So how can we use that? Well, let's imagine that we were here, looking at the sun this way. As it wobbled, sometimes when it was wobbling, so if we do this again, and we increase the speed one more time, it wobbles left and right a little bit, but also it's wobbling a little bit towards us and a little bit away from us, and a little bit towards us and a little bit away from us. And astronomers can be very clever about the fact that when something in space is moving towards you or away from you, you can look at the wavelengths of its light. And now notice that when something is in space, or even on Earth and stuff, and moves towards you at a very fast speed, and they have to be very, 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 the speed that this star is moving is not a huge distance, but it's enough that you actually can see that the light gets pushed to slightly shorter wavelengths. We call this blue shifting, and it gets pulled to slightly longer wavelengths when it's moving away from you. We call that red shifting. It happens in the stuff that I do with galaxies all the time, but with stars, you can see this. The fact that the star is moving towards you, away from you, towards you, away from you, towards you, away from you as it moves around like this means that you actually be able to measure how fast it's moving, and over time you can chart the speed and infer that there must be other planets around it that are causing it to wobble back and forth. So this stellar wobble, so we call it, it's the fancy technical term, the reflex motion of its planets infers that it has planets. And so all astronomers need to do is go and measure a star's motion to see if it has that. This is dependent on how close the planets are and how massive they are. If the planet is bigger, more massive, it'll cause more of a wobble. If the planet is really, really, really far away, it'll cause less of a wobble. It's really close to cause more of a wobble, which means that we're very biased with this method in finding planets that are close by the star and very, very big. So, we talk about these, we call them hot Jupiters. Jupiters that are really, really, like planets like Jupiter that are really massive that cause a lot of wobble. And because they're very close to their star, they're very hot. And so when we start finding planets using this method, we found a lot of really close by Jupiters, around their Jupiter-style planets around their host star, which is good. But the question you want to know is, how do you find Earths? That's a little tougher with this method because you have to have an incredibly, incredibly sensitive, incredibly good detector that can look and see the tiny amount of centimeter per second motion or whatever. There's a super tiny amount of motion that the star does when it wobbles, right? And you have to watch it over a long period of time as well, because if you want to see the whole of the period, if the planet is really far away, like if it's Earth, you want to watch the whole period, you need to monitor it for an entire year to see the wobble as it gets closer and farther away. And it's even harder if there's other planets that are bigger because they have bigger effects on the star, which means the effect of an Earth is masked out. But that's the radial velocity method, because you're measuring the velocity towards us and away from us as the star wobbles in space. All right. Now, The second method is the more successful method, and I think is kind of a very clever method. So let's go back to Earth. I'm going to turn the orbits off here really quickly. We're going to make sure we're at normal speed. We're now good. And what I'm going to do is I'm going to look. Whoops, I've turned off. What I'm going to do is I'm going to look and see if we can find a Kepler object. And I'll explain why in a second. So let's look at Kepler One. Nope. Kepler One. Let's center it. Okay. So if we were to turn on the Cassiopeia, you can see that I'm looking right now in the constellation of Cygnus the Swan. Really fantastic constellation. And this part of the sky right near one of the wings is what we call the Kepler Field. And a telescope went out into space called Kepler, and it looked in a very specific patch of sky over a region that's larger than the full moon. And what it did was it looked every night and started taking pictures of all the stars. And it was looking for a very specific thing. So what I'm going to do now is I'm going to zoom in on one object in this field, right? So we're going to zoom in on one object in this field. Here it is. There it is, right there. Whoops. Getting closer. All right. So this is Kepler One. It's a yellow dwarf, a G-type star, like our sun, but maybe a little smaller than our sun. Its mass is about 0.98 of our mass. It's pretty neat. And if I turn on its, and what's neat about this, if we just go there, let's put this back. I'm going to turn off the lines here. So if we go there, you'll see exactly what, it's better than if I use the telescope and zoom in. If we go there, you can see what's neat about the stars that are in this field that were discovered by Kepler and how they had planets. So here's the star. And what I'm going to do now, I'm going to get really close. Whoops, we passed it. Let's drop the speed. Let's drop this a bunch. Oops, wrong thing. There. Oh, I guess we don't want to do that. Maybe we have to get really close. Aha. So, right here you can see Kepler 1b. Whoops. Which is one of the planets in the system around Kepler. And if I let time go on, watch what it does. Whoop. Let's make time go on a lot more. From the point of view, I think I'm out of whack with it a little bit. So notice it's going around. Boop. So there's the Kepler planet, and it's going around, and it's not going to produce a huge amount of reflex motion, but for a little tiny bit of time, notice what it does. And I'm going to drop the brightness even more. Whoop! Did you see that? Let's zoom in. Boop! There it is. Let's zoom in a little bit. Boop! So let's drop the speed a little bit. You can see it wrapping around the back here. And then it's going to go right up in front, and I'll pause it. Okay? This is how it's seen from the Earth. Okay? Ready? Boop. It's what we call transiting the star, meaning the light from the star is blocked because the planet is going directly in the line as it orbits around. So from our perspective, this planet is going directly in line with the star around it in its orbit, right? And I can rotate this so that if we wanted to make it so it was, made more sense for left and right like we normally associate orbits. In this time, what it's actually doing is it's blocking some of the star's light. So if we make time go on a little bit faster again, here it goes. Now we have 100% of the star's light, right? As it goes behind, the star's light gets a little bit brighter, because it has a little bit extra, but we'll talk about that in a second. 100% of the star's light, and then suddenly, as the planet gets closer to transiting as it goes around, We'll turn this on, make it go just a little bit slower. The planet is starting to get a little closer, a little closer. All right, here we go. You can barely see it. Now the star's light dips and stays fainter than it would be otherwise, and then it rises again, back to its normal level. So if you were to watch this star, take pictures of it every couple minutes, or every hour, or every, and you get lucky, you might catch a time where the planet was moving right in front of it, and the star's light, it would look like this bright, same brightness, same brightness, same brightness. It would dim, and then would go back up. And then would dim, and then would go back up. And that would tell you that something was blocking the light of the star in a characteristic way. It would tell you how big that was too, because if it was a bigger thing on it, you would be able to, it would block more of the light, right? And so what you're seeing here, if we make the time go by a little bit faster, is just one of the types of planets that was discovered with this method by the Kepler telescope. Boop, it saw that. And then later, it would go back, keep watching, keep taking pictures of it, keep taking pictures of it, keep taking pictures of it, dim. Same brightness, same brightness, same brightness, same brightness, same brightness, and dim, right? So this is called a transiting exoplanet. And if we zoom back out, we really fly away, from the Earth, all you'd see is the star. And it's a little hard to see because they don't simulate it very well here. But in a hypothetical world, you could look through this and see that like the star's light, if you took pictures of the star, it'd be dimming just a tiny bit, maybe 1%, as seen from the Earth. 1% of the light, but we can measure that. And so this is called the transiting exoplanet method. And it's the way that Kepler employed, it was a method that Kepler employed to find planets, because it looked at a giant patch of sky, hoping, and looked at all the stars every night, hoping to somehow capture this process in action. And it found thousands of planets. This method also requires a planet to be very close to its star, or to be bigger, similar to the other method, because then it will dim the light even more, right? You have to have a very, very sensitive, we call photometer or camera, that can like get that 1% light or less. Earth's will make even less. So Jupiter makes a 1% difference. Earth is a fraction of a percent, which is really difficult to do, but definitely doable. Especially as you look at it for longer and longer and build up better statistics. And so if I go back to this chart here, the green is radial velocity, or is transit, and the red is radial velocity. And so you can see that while radial velocity, some number every year, we really, in 2014, 2016, like there were some big releases of Kepler data, and people started really discovering these planets. And it's pretty amazing what we discovered, right? The problem is, you're saying, well, we got all these planets. Have we discovered any Earths yet? Have we discovered any, planets like Earth? Well, there's planets that are close, but the problem is that they're generally around stars where we don't know if there's a lot of possibility of an existence, and it's really hard in some cases to go back and look for these planets and understand what's going on with them. This is one of the things that the James Webb Space Telescope that I work on will be really poised to do, which is look and see for some planets what's in their atmosphere or whether or not they have an atmosphere. How would you do that? Let's go back and let's look again at Kepler 1b here. Now let's look at it at a very specific, whoa, I need to stop doing that, at a very specific time. So I'm going to zoom in, and I'm going to raise the temperature, raise the brightness a little bit. And let's go time-wise again. So the planet should wrap itself around in a second. There it goes. Up, 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 up. So what happens is, I may not be able to go back in time, can I? I can't go back in time. Nope. But I can go and try this one more time. Let's zoom out. All right. So I'm going to zoom in a little bit. We're going to get it right when this starts to happen. This is a pretty cool effect. Matthew Sorensen has a good question. What planets in our solar system are observable this way from another system? Let's do the same thing in a second. We'll look at this. So if we zoom in again, this is like a pretty amazing period right here, where as we get closer, there's like a tiny, tiny point right, bam. So if I take this, look out right here, and zoom our little telescope in, for this one brief moment, notice, it's hard to see, notice the atmosphere of the planet is just barely passing. Light from the star is passing through the atmosphere of the planet, meaning that light from the star is interacting with gas in the atmosphere of the planet, and we can, for this brief moment, as the planet goes in front of the star and then leaves the star, understand what's going on in the atmospheres of these stars, of this planet, which is incredible. To be able to understand the atmosphere of a distant planet is very, very difficult. You have to have very specific timing, and you have to have really, really good job of removing the light from the star, just so that you get the light that passes through those. But in the infrared, the light that you might be able to see that from the star that goes through this will help you understand whether or not there's water, oxygen, methane in the atmospheres of these planets, which is pretty cool, right? So the radial velocity method provides a huge amount of information about the planet and potentially about its atmosphere. It's really cool. And we've been able to do, you can see sometimes if there's multiple planets in a system, you could be able to see multiple dips, right? At the 1% or in fractional levels. So you'll see, there's a bunch of planets, because it turns out that generally in a solar system, like our own as well, generally the planets are aligned pretty well, and so they'll tend to block. So Matthew Sorensen asks a really, really good question. And I don't know if I can answer super well, but if we go back to the sun and we zoom out, so I'm going to make this back again to this. We zoom out, let's turn on our handy orbits. All right, so here's our solar system. So notice if people, all the stars that are in this part of the galaxy looking down on our solar system, they could not use either of these methods, because the star wobbles this way, it doesn't wobble towards or away, and none of the planets transit. They don't go in front. They all go around like this, right? So if we were looking at stars like this, it'd be hard for us. This is a good method if you want to take a direct image of the planet, because you can be far enough away, generally on average, so you can find it. But you can only do that for really, really far away. And so if you're far away alien, you might be able to take direct images of Jupiter or Saturn. It'd be very difficult unless you have very good technology to find or closer in planets. But let's go and do this. Let's zoom and look right here, down along the edge, to see, can we do this for our own solar system? Okay, so I'm trying to get on the edge. I'm going to rotate it so that we're looking from the side here. And let's once again zoom in using our telescope. So let's center this and zoom in using the fancy telescope. The green lines again represent the exact orbits of the planets. Okay? And so if we zoom in so that we can see the actual disk of the sun, you can see right now that only one or two of the green lines actually go in front of or behind the sun. Right? Most of them, the solar system doesn't have enough of an alignment for us to get a really good job, do a really good job of this. So it'd be pretty tough, right? But if I, look up or down, maybe I can get closer to the actual plane. Let's drop the velocity by a little bit. Whoops. We can really see if we can find a better lineup. We could see maybe this. Like, you can see that these lines don't all exactly line up in front, right? The solar system's kind of out of alignment with all the planets. If I increase the speed more, let's get this really cranking. There's one. There's the Earth, or there's another one going in front, right? Ooh, one just barely missed. Here's one coming. Stop. Okay, so what planet is this? This is Jupiter, right? So here's Jupiter right here. So zoom in a little bit more on the sun. And here's Jupiter coming in front. And so if we watch, you can see that from this exact perspective, Jupiter, you can see how many hours this dip is, right? There's the start of the dip, which is at 1433, right? And it ends at 1631. So it's a couple hours of dip from this distance, right? But that's it. And Jupiter generally, maybe Saturn, probably our best shots for an alien to see this at the moment. It'd be very, very difficult. If they were very lucky and had the ability to see, like a really, really good telescope, and they were at an exact orbit. Like if I do this and we go Earth, and look, we highlight that one. Let's zoom in one more time and see where's the Earth. There's the Earth. Earth's right here. So let's go up a little bit. All right, so now there goes the Earth. We'll see it when it wraps back around. I just want to make sure that it actually... Where's the Earth? Hello, Earth. It must be... Oh, there it is. Okay. Whew. Really flinging around. Up. It'd be very tough, is what I'm trying to say. I don't know why it's hard to find the Earth at the moment, but I think it's because it's way out there, and I'm only going hour by hour, and I have to go an entire year. But anyway, the answer to your question is you got to be very lucky. So here it comes. There's the Earth. Getting closer and closer. If I have to go up a little tiny bit, I think, to get the exact lineup from this perspective. So if we go a little faster, we're getting closer. Here's the Earth and the Moon. And almost. Oof. So here's the perspective that an alien would have to have in this direction. So if we keep zooming, if we keep turning down the brightness. The Earth is passing in front, Matthew. Right now. And so the thing is that it's pretty tough. It's pretty tough to see. If I turn off my orbit lines, it's really hard. You can see that it's there. There's the Earth right there, that little tiny dot. Way different than the planet I was showing you earlier, because it's much farther away and small, right? 1 million Earths could fit inside the sun. So that's the Earth transiting the sun, making this tiny, tiny fraction. So probably pretty tough to observe that from far away, right? From this perspective, it looks just like any one of the other sunspots. And so the amount of brightness that the sun would change by sunspots is, similar to what we would get with just the Earth transiting. So you got to be lucky that you get a Jupiter-sized planet, because that's like 1,000 times, 100 times bigger, right? Or sorry, 10 times bigger, 100 times area-wise. But we've done a pretty good job of finding planets in the two methods that I said, and we've taken direct images. And we're doing better and better, and there are new telescopes that are, because the real goal is to find an Earth-type planet. Because once we find that Earth-type planet, my gosh, if we find Earth, we're going to train Earth, like a planet that is similarly in a zone where water can be liquid. It's not too close to its star, not too far away. Something where there might be an atmosphere. We're going to start really observing it a bunch, right? It'll be a target of most every large telescope mission, and maybe even new telescopes we built and launched just to observe it, right? We'll start sending signals there. It'll be a real big deal. The problem is we haven't found that right now. We found some promising candidates, but even those are pretty big, right? So in the last 20 minutes, I want to show you something cool about this program. So let's go back to now. Let's change this back to this, and we'll turn this off, and we'll do this. I guess we'll stop tracking. So here's the sun, surrounded by all these other stars, right? What's neat about so we when we look at the stars in our solar system, is we find that pretty much every star most likely has planets around it. The problem is that it's really hard to find those planets. So, but when we get better and better technology, we realize like, oh man, planets are everywhere. They're around almost every star. Space Engine has a nice catalog of the real planets we've discovered in it. My office mate, Thomas Beatty, has discovered a number of planets, and his planets that he's discovered are in this program. Pretty cool. Nothing I've discovered is in the program because galaxies aren't nearly as trendy as stars or planets. But the creator of this program recognized that you can't just put the things you've discovered in. You have to put in things that kind of simulate what we might expect, right? So here's something neat. Let's just pick a star at random, right there. How about this star right there, okay? So at 73 Ceti, we're going to go there. Here we are. Boom. It's a B-type star, a blue supergiant. Very, very, very bright. Probably not a great place to find life, but this program simulates what might be there. If we look at its solar system chart, we see that, there's some planets. Look at the planets here. Wow, right? So if I click on it, this one here, planet, I guess it's Psi 2 Ceti 1 is a Taurid super Neptune. This is a Taurid sub Neptune. These planets here are probably not like, they're hot, Taurid meaning very hot. Like this planet is, its semi-major axis is some number of miles, not AU. It's just, like some number of miles. It's very close in, right? These planets are probably just completely baked if they, hot Neptune, hot arid Terra, warm mini Jupiter. Here's a hot super oceanic super Aquaria here. Planet Psi 2 Ceti 8. This planet probably doesn't exist. We can go look at it. We fly by all the other planets as we get out there. And see this planet that they've just simulated here. Completely simulated planet. We don't know anything about what it actually is like. And there it is, right? Beautiful rings. We can look, it has, oceans on the surface and a big, crazy amount of, cyclones and, hurricanes. Probably life wouldn't want to exist here. Not the greatest place. Its semi-major axis is 8 AU, meaning it's 8 times farther from the sun than we are. Somewhere in the asteroid belt for us. It has a very UV bright star, so it probably would not, a star that doesn't live very long. So if there is life on this planet, which doesn't indicate there is, it would be baked away by the UV light, which would be pretty bad, right? But here's a question. Can we find a star, let's find a white main sequence star. There's an F-type star, kind of like our sun. Our sun's a G-type star. This is a little bit brighter. Can we find a star and look around and see, can we find a star that might be like, so let's filter our settings right now. I want to find a temperate marine Terra like our planet, right? And I want to find this planet, this object to search planet only. And I want to say it has a diameter. No, I want it to have like a mass of 0.5 to 1.5, so very similar to the Earth, right? So let's look at this right here. Let's go to this star right here. Again, this is probably a real star, Hipparchus 19762, but it probably doesn't have this many planets. It's a K-type star, so this is a more red star. It's much cooler than our own sun. Its mass is 0.8, 80%, 81% of what the mass of the sun is. And let's look at its planets. Let's look at its planets like this. Because I've been told that there's one planet here that might be of interest. So there's the hot arid subterra, a warm Neptune, a temperate lacustrine Terra with life. We've got to look at that one. A temperate mini Jupiter with life, a cold arid Aquaria, a cold sub-Jupiter, a cold arid sub-Aquaria, and a frigid Jupiter. Let's look at this planet right here. A temperate lacustrine Terra with life. I wonder what lacustrine means. Lacustrine means relating or associated with lakes. Oh, so it's like a mini Minnesota. Let's get there. Boom. Wow. Here we are. Look at this. It's ringed. Welcome to Lake Planet. Welcome to Planet Minnesota. Rings. Temperate. Organic. Multicellular. Marine life. Let's land on it, huh? Whoops, nope. Let's land on the object. I went to that. Here we are. It's like we're standing on our own planet. A lot of desert here. Let's fly up in the air. We'll kind of zoom over the surface. It's got some mountains. This is, again, all simulated. But these are the types of planets that we think probably do exist out there. Planets that are like ours, but very difficult to discover, right? Very, very difficult to discover. So when I say lacustrine, it means that there's not a lot of ocean. There's probably a lot of lake. And I'm just not seeing any of the lakes immediately right now. So maybe not like Jupiter or Minnesota, because I would hopefully see more lakes. But notice it has an atmospheric pressure about our atmospheric pressure. The temperature is 61 degrees Fahrenheit. Not so bad. Not so bad. This is pretty Earth-like. It's 79 days around its own sun, and its solar day is 238 days. So it rotates once every 238 days, which is maybe means you get long, long days, right? But apparently, marine life lives on here. If we go to the next one, this Taurid mini Jupiter, pretty cool. We can see that apparently this also has aerial multicellular life in the atmosphere. It has atmosphere filled with multicellular life. Well, again, it's simulated. You know, it's completely made up. But this is also something that might be able to exist, right? Which is pretty amazing. So this would be like a solar system similar to our own, right? Mercury, Venus, Earth, like a Jupiter that kind of has like atmospheric life. Even its own cold sub-Jupiter, which I guess we call maybe a Saturn, because Saturn is like a sub-Jupiter. Look at this. Wow. So look at this Saturn like. It's got rings like Saturn, and it has a whole bunch of moons. How many moons? Well, if we go back to this, you can see that they've simulated at least 95 moons around it, which is pretty incredible. And this one right here, which is kind of like the moon, lots of really crazy impact craters, a cold, arid Aquaria. So it must have a bunch of ice around it, right? Pretty neat. And it's got its own moon. If we go back to this planet, the Earth-like planet, it has 3 moons, but they're little asteroid captures, so they're not super exciting. I just like that it has these crazy rings as well. I'm very jealous of any planet with rings. But that's pretty neat, right? We could look for other planets like our own. We're still trying to find ones. Let's see if we can find a G-type star. There we go. Wait, oh, there's the G. So, boom, here's another one. Let's look at its solar system viewer. G-type star like our sun. We've got hot airless sub-Terra, hot arid Terra, temperate arid Terra, cold arid Terra, temperate marine Terra. Oh, a little bit Earth-like, also with rings. We got so unlucky that the Earth doesn't have rings. Cold arid super Aquaria, frigid airless sub-Aquaria, frigid area Aquaria. So you can see that, you know, this has got like some pretty crazy cold spots on the surface, and a frigid area Aquarius. This one doesn't have any gas giants. It looks like it's got a bunch of, you know, planets. So this temperate marine Aquaria is like our planet. Let's land on it. I like landing on other planets. It's something you don't really get to do very often. But here in Space Engine, you can do it all you dang want. So, this may not be the greatest place for us to live. It has 400 times the atmosphere of our planet, and its temperature, but the temperature is only 65 degrees Fahrenheit, not so bad. It just has quite a bit of greenhouse efficiency, so it's got a lot of carbon dioxide in the atmosphere. So this might be like a Venus-style planet, but not so, you know. It's located at 2 AU, so 2.5 times farther away. Got very thick atmosphere, so probably wouldn't want to live here. Probably not the best place for us to live if we were like trying to find another planet like our own. If we go and look at this, and I add one more thing to our filter settings, can I add an Earth, an ESI, organic life, multicellular, exotic life? Let's just do exotic life, not tidal locking. I want to do rings, yeah. Let's change this. Filter. 0, 0, it's looking. Not finding anything at the moment. Huh. Well, this is maybe the closest we're going to get. We got life on 4 objects. So let's turn this thing off and go back over here. This one, hot Neptune, Taurid arid Terra, hot super Jupiter, warm super Neptune, temperate sub Neptune, cool Arid Aquaria, cool Neptune, cool lacustrine Aquaria with life. So this is very similar to the one we saw earlier with lakes, right? Frigid mini Jupiter, and it must be that some of these have life as well. I can't click on them and find them. Temperate airless mini Terra, you know. More life, subglacial life. Wow, there's all sorts of life on this. This is like the moon of Aya or Europa in our solar system, which we think may have life on it. So when people ask me a lot of the times, how is it that we're going to find life on other planets? Well, it turns out you got to be able to find the planets to begin with. Then you got to be able to find the evidence that life exists there, which is tough. And also, the life might not even exist on the planets. It might exist on the moons around the planets. And it might not be life that is outward facing, right? We're plant life that lives on the surface. But it could be life that lives underground or life that lives under large amounts of glaciers, in which case they just wouldn't have a relationship with the sky like we would. There'd be no reason to go out to the surface because it'd be too cold, and whatever medium that they needed to survive wouldn't exist. And maybe they have astronauts like we have astronauts that would want to escape the bounds of what they thought they could and explore other places, but it'd be pretty tough, to get out and if you've only lived in certain environments. We're very lucky that we live on a planet where we can put rockets and explore outward, but maybe life is not as common as the game thinks, but I don't know. Or maybe life is just very simple everywhere. This is tough, right? So if I put this and I say I want to do let's do 500 parsecs. Let's see if we can find anyone that satisfies our... It's tough. It's really tough. There's a lot of cool planets, but none of them satisfy all of our... If I change my filter settings and I say, I don't know, diameter, temperature, atmosphere, maybe I'll turn the mass off. Is that going to change anything? Any objects? Doesn't look like it. It looks like we've got a very, very lucky Earth, Well, I was playing this game a couple months ago with Nick Brecken, Twitch streamer Idle Thumbs, and we happened to find like a perfect planet, like just randomly when we were flying through Andromeda. It was pretty incredible. If I go to a different place, let's close that. Let's get out of this mode, and go and look at some other galaxies. Let's fly out of our galaxy here, because we were only looking in one tiny chunk of our own galaxy there, right? And I go to like some other part of the galaxy, say like right over here, and I do the same search. Boop, 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 boop. Are we going to get luckier in this other tiny chunk? Gosh, 25 planets in a system. Holy cow. That might be worth looking. Oh, hey, wait, we found one. Oh man, this is so exciting. Oh, look, orange dwarf. All right, give us some Earth. I want some Earth-like. Oh, I see it. I see a temperate marine super Terra with life. Oh, let's go there. This planet is 3 times the mass of our own planet. And look at it. Islands in the stream, man. Wow. Look, I call this New Zealand. Ooh, and we've got like a Mauna Kea style, volcano here on the surface. Pretty incredible, right? Welcome to our new planet. Planet RS 84963161840462053395. The new planet we can all go live on. A planet. Let's actually land. Let's land right over here. So let's land. Probably gonna land in the ocean, but we'll make do. Oh, look at the beautiful water. Seas are composed of water, atmospheric composition, nitrogen, oxygen, and water. It's got 15 times the atmospheric pressure, and the temperature right now is 55 degrees, so it's a little cold. Maybe it's because I'm so far away from the surface. Ooh, we're under the water there. Here we are. But, nice greenhouse efficiency there. Looking out at the atmosphere and the clouds on our new second Earth here. Earth's similarity index is 0.898, so it's pretty close to the in how it is kind of like the Earth. I think it might be tidally locked. I think that's why it says solar day equals infinity, which is a kind of a bummer. But its orbital period is 95 days and its rotation period is 98.5 days. So yes, one side always faces the sun and one side there's a side of perpetual day and a side of perpetual night. Maybe not my favorite place to go visit, but neat to be here for a little bit. And what does that mean? Well, if we look up, we sit here and we land once again and look up and we just let time go on. We'll never have nighttime because the sun never sets. The atmosphere continues going, but the sun never sets. So we call tidally locked, meaning one side, this side, will always be pointing. You have the atmosphere, the clouds are moving, but as this thing goes around, you can see its moons going around. As it goes around, this side will always be pointing towards, if I look at this, and I zoom out quite a bit, I really increase the speed, one side always stays pointing towards the sun, right? You can still see the same, things as it goes around the star, stays pointing. Whoops. Well, that means that one side is perpetually dark here. So this would be the side you'd go on if you want to have nighttime, and the other side is perpetually daytime. Pretty cool, though, that we found our own little new planet. Not a really fun one to potentially live on, but unless you were like living on in Snowpiercer, there was some sort of round the planet boat that would go between day and night very quickly, which might not be the worst idea. But that is what I wanted to finish on. If there are any other questions, I can answer them right now. Otherwise, I hope you've learned a little bit about how we find planets. You should continue to look this up, and you should always investigate when someone talks about finding new planets. Was that a radio velocity planet? Was it a transit planet? Was it a directly imaged planet? And so, I could look up directly imaged planets like Fomalhaut. We can find Fomalhaut B. And so this is a picture here. If I put this over in this other... Let's look at this picture right here. I'm going to go back and bring up the window capture. Boom. All right, so here you can see the star Fomalhaut is so bright that they've had to remove the star's light in this picture. That's why it's got all these rays, because they didn't do a perfect job of removing light. They did a great job, let me tell you. And around it is this ring, and that's dust and gas that's around it. We've got the same thing around ours. And if you look inside, you get pictures in 2004, 2006, 2010, and 2012 of a little planet, Fomalhaut B. So you're actually seeing the planet, a direct picture of the planet. But it's incredibly hard yet to remove the light from the star. Very, very tough stuff, right? So next time, in a couple weeks, I'm going to do this. I'm going to talk about galaxies, which is what I actually do. I love talking about planets. They're pretty cool. I love flying them. But I want to talk about galaxies. And I'll be able to use Space Engine, but I'll also want to talk a little about other galaxies, and we might get into black hole stuff. So I might start next in a couple weeks and talk about the Milky Way. We'll talk about the structure of the Milky Way, the types of stars in the Milky Way, why it looks like it is, what's going to happen, and we'll talk about the black hole at the center of the Milky Way, which is very cool. But until then, I hope you guys had a fun time. If you have any other questions, you should please feel free to ask. You should follow me on social media. I'm on Twitter here. At Kevin Hainline, Kevin_Hainline, and Instagram is Kevin Hainline, just all one word. You should, it's right here. You should follow me. I do this every other week, so I'll do another one in 2 weeks, and we'll talk about the Milky Way then. These are all archived on YouTube, and I really had a fun time. Thank you, Matthew and Craze, for asking some questions, and I hope you have a wonderful rest of your evening and stay safe. Wear masks if you go out. Try to limit the amount of exposure you have with other people. Let's try and stop this insane virus from spreading. Bye, everyone.